This is my fourth video on geophysical PPV monitoring, which is going to be on setting up a test program. The third video on sensor orientation will follow this video, as I realized this setting up your program video is probably good background before addressing sensor orientation considerations. Now, to cut to the chase on setting up a PPV program, design your source locations at a good range of offsets and measure the vibrations. Make sure to sample the steep part of the energy decay curve, and that's it. End of story, that simple. But for those looking for more detail or a good place to start, stick around. Now, why this video series? This is the thing. There seems to be little documentation on geophysical PPV monitoring, and thus we may all be inventing our own wheel. These are some thoughts for you to discard or to build on. You can pause the slides to review the actual detail. There is a Word document about some of this that I will try to link in the description. It does not exactly follow this format, but the gist is there. There is a slide number in the bottom right-hand corner of each slide in case you have a comment or specific question. I can be reached via LinkedIn at Doug Iverson or through the comments in the video. Comments or questions in the YouTube comments section may help me or others, so I would encourage that method. And finally, to close out this intro, there's a great deal of PPV information at the Canadian Association of Geophysical Contractors website. If you search seismic setbacks, info will be in the description. Now, if you have no sensitive structures in your work area, then vibration monitoring might not be necessary, but there's still valuable information that can be obtained. PPV monitoring can be used to reduce the possibility of damage, to ensure you're compliant with any specific regulations, and to perhaps protect you in the event of a damage claim. If there are regulations, they may either be energy size and distance based on a scale distance, could be defined by a peak particle velocity, or they could just be set by a feeling. If there are no regulations, then it could be up to you. In either case, regulated or not, you're still liable for any damage. This will focus mainly on dynamite, but the process is fairly similar for vibrosize. For vibrosize, I would recommend testing a suite of offsets with the desired high drive level, and then select a drive level at 40 or 50% of that and repeat the test. So, slide 1. This is an example of the Alberta scale distance requirements for structures that was implemented in 2022 after significant testing and consultation. The structures were grouped into different categories. Structures considered sensitive, such as residences and their associated water wells, were given a scale distance setback of 45, and more robust structures, such as high pressure pipelines, a scale distance of 22.6. Now, it would actually be 22.5, but just because of rounding errors, it changed the value to 22.6. Now, the concept is this. You can load a 12 kilogram charge 200 meters from a residence, but with consent, you could get in as close as 16 meters with a 0.125 kilogram charge. Now, this is significant for shallow imaging and operational efficiency. Often, when we had a gap of this 200 meters to 16 meter range, we may miss several potential source points. These missed source points were often offset to new locations, but did nothing for the shallow coverage. The cost benefit of relocating these missed points was marginal at best. So this next slide is the Alberta setbacks for non-explosive sources. Again, we have the same structure categories, but we define the vibrators by fundamental force. Previously, the requirement was vibrators could be no closer than 100 meters to a water well, but there was no specification on the number of vibrators, the size of the vibrators, or the drive levels. So this is an improvement. Now, at the top of this slide are PPV thresholds adopted for the specific structures listed. And at the bottom right is the USBM Osmery Z-curve, which is often used for compliant vibration levels for residences. It should be noted that vibrations above the line does not mean there will be damage, just the possibility of cosmetic damage increases. Okay, slide 5 here. This slide you might want to pause, but in general, the source energy size and the offset distance are the two most important factors when it comes to vibration levels. Other lesser factors could include the charge composition, soil type, charge confinement, charge depth, just to name a few. As a simplistic generalization for source energy size, with dynamite we mean the charge size, and with vibrators the fundamental force, which is a combination of the hold down weight, the assigned drive level. And here's slide 6 with some additional dynamite information that demonstrates the areas of inelastic and elastic deformation around the charge area. Now slide 7. These are some US data that we're going to review in more detail shortly. When we look at plots of vibration energy, peak particle velocity, versus distance, we usually look at them in linear and logarithmic scales. The linear graph on the left is very intuitive for demonstrating how fast the energy falls off with distance. The logarithmic plot on the right makes it easier to predict the expected PPV at, say, a 1.5 foot offset. Of course, the equations are the same and could be used to predict the PPV at the different offsets. With slide 8, in testing, it is important to capture a good range of data that actually defines the energy decay curve and is also within the expected range of our operation. The red oval in this example is to show the offsets within the area that is pretty significant, as it's the steepest part of the energy decay curve. Then at the farther offsets, as shown in the green oval, the energy can be quite low, that it's not as significant, but for testing we should capture these data. That helps us better understand what we have, and it's good to capture data down to about 1 millimeter per second. Often in geophysical we deal with one charge size throughout the project. Thus we can plot PPV versus distance. However, when you want to compare with other charge sizes, we use a concept called scale distance. Scale distance allows us to plot the PPV vibration against one variable on the x-axis. That is the scale distance. And the scale distance is the distance divided by the square root of the charge size. The idea being the vibration levels for explosives are essentially equal when normalized like this. Basically, a 4 kg charge at 90 meters has a scale distance of 45. A 0.25 kilogram charge has a scale distance of 45 at 22.5 meters. That is 45 times the square root of 0.25 kilograms. When the scale distance is the same, we expect for the most part the vibration levels would be similar. Using scale distance is a standard way to display these data, although for individual tests you could just use charge size. Now before we start with the actual test setup, this is where I would recommend starting. I'll try to put a link to the article in the description. If I have no luck, reach out to me in the comments and I will find a way to get it to you. It is from the Denver Geophysical Society, from the record from October of 2014. Now jumping into the feature article here, there are two graphs from the report and these are very good starting points. On the left is the dynamite results, and on the right, the vibroseis results. The details are given in the article, and both sets of data have a reasonable correlation value. The PPV data are in inches per second and feet. These data represent a fairly good diversity of results. However, you should do testing in your own specific area. What is unknown about the dynamite data is, did they use surface distance from the shot hole to the sensor, or the hypotenuse distance from the depth of the charge to the sensor? And if they had a pattern hole, where did they set up the sensor? Was it inline or crossline? This is where the data came from the study. I've also seen some data from New York, and it's fairly consistent with these Western US data. And I've shown up above where Alberta is, and it's just above Montana, and we'll review data from there as well. For both data sets, we are given the equation for the respective 95% confidence lines. For the dynamite case shown here, we know the slope is defined by the minus 1.34. We know an average trend line, which they show would be parallel to the 95% confidence line. Thus, we can reverse engineer the line equation by estimating some values from the graph and then refining them. So that's what I've done, and the graph on the right, I'm going to slide over to see what the fit looks like. And here I have superimposed the engineered values on the graph. You should do your own work, but the equation of the average trend line is 86.242 times the scale distance raised to minus 1.34. This is a good data set for you to compare your US results with. This plot shows the two plots in a linear and log format ranging from 8 to 200 plus feet. But what can we ascertain from these two plots? Well, it's easier to see on the logarithmic plot here on the right. But for the average trend line, we know that the minus 1.34 was equivalent to the slope of the line, and the first part of the equation, the 86.242, is the intercept at a scale distance of 1. So as you see, as I extended it there, it hits 86.24. That's good to know. Now, I'm sure it's obvious to many, but it actually took me quite a while to get this. We also know that the scale distance plots on the left is exactly the same as a 1 pound charge plotted versus distance, as the square root of 1 is 1. So we know those are the same. And from this, we can deconstruct different charge sizes versus distance. What we have to be careful of is this. We do not know the actual range of offsets used during their test, and especially the near offsets. For that reason, when you test, your offset distances should extend beyond the range of vibration thresholds that you want to manage or consider. You should not extrapolate predicted PPV values beyond your test range, as it would be high risk to extrapolate a value for a 2-foot offset if your data only ranges from 8 feet to 200 feet, especially in the steepest part of the curve. And slide 18 is an example of that. These are over 1,000 data points collected with a 0.125 kilogram charge. And you can see if we isolate the offsets greater than 110 meters, which is in the green, we get a very different average trend line than if we use the data from the 13 to 60 meter range. The risk here is this. If you incorporate all those farther offsets into your data to generate an average trend line, it will tend to drive the average trend line down, which predicts a lower PPV at a specific offset. These are strictly production data, and we were mandated to stay at least 15 meters away from structures. So just a quick compare of deconstructing the Matheson vibrator data compared to the 1 pound charge in distance. Now, my experience is these curves tend to be more parallel, but I'm not sure where the sensor was in relation to the 4 vibrators. but I'm just putting it so you can have a look at it. So now let's do a quick bit on Alberta. Industry did a fair number of dynamite tests from 2013 to 2021, which were located by the red stars. The charge sizes ranged from 0.125 kg to 4 kg, but mostly in the lower charge sizes. The named areas on the maps are from a legacy 1987 test that at the time we did not know existed. So this graph is of the industry data in metric, so millimeters per second, and scale distance in meters and kilograms. The average trend line and the outer trend lines are shown, and these data are presented from the surface distance of the dynamite hole to the sensor. Then this is a bit more info on the charges used in the 1987 test. There is a greater range of charge sizes, pattern holes, different charge depths, and definitely a larger geographic area. And then here we are going to show the industry tests and the 1987 data points with their average trend line. As expected, the average trend lines were very similar. Those are the black and green solid lines. The data in 1987 were collected with no decimal points, which is why the data kind of lines up and looks a little bit truncated. And so now from that 1987 data, we have to put in its outlier, which exceeds the previous outlier that we had. But that is fully expected based on the greater geographic diversity, the wider range of charge sizes, pattern holes, hole depths, and recording in summer and winter. And so when the Alberta setback regulations were updated, that higher outlier value was used. And then I'm going to put on the US data here. Those are the red and the purple line, the red being the outlier, the purple being the average trend line. And given we don't know everything about how they recorded the US data, this is actually not a bad fit, and we certainly expect some diversity. Now, one of the things that I do when I'm reviewing other PPV information that I'm researching, I see to how it compares to what I expected. Now, this is a paper of doing PPV testing in the Assam region of India, some 11,000 kilometers away from Alberta. And in this paper, there were concerns about damaging some of the local structures, which had tin or thatched roofs that were constructed with bamboo walls that were often reinforced with cement. So on the left is a list of the structures of concern, and below it are the PPV recordings with the different charge sizes, hole depths, and offset distances. I have taken these data and plotted them with our Alberta data, and you can see how uncanny the fit actually is. Okay, so why do we test? There are many reasons, but let's say we are going to use a USBM OSMRI chart as our threshold for residences and sensitive structures. Thus, we need to know where we could possibly be in non-compliance. In particular, testing can really help with understanding this area below 49 Hertz on the Z curve. And from what I see, a great deal of the US work is that many operators defer to a maximum of 0.5 inches per second or 12.7 millimeters per second, which falls across the USBM plaster threshold. This 0.5 inches per second is also referenced in the Denver Geophysical Society paper that I mentioned earlier. I attribute this to a higher potential of litigation in the US, but I could be very wrong. Hopefully, this may garner some comments or discussions. But obviously, if you kept it below the lowest level, which could be 5 millimeters per second, or the 12.7 for that plaster threshold, kind of above 3 Hertz there, that might help protect you more. Not sure. In Canada, much of our work is pre-drilled, so we have to pre-plan our setback distances early in the program. This is where testing is handy, especially if you may want to use a smaller charge to get closer to structures so that you can image shallow. Fiber size is of course different and affords more real-time monitoring component, albeit with some issues that will be addressed in segment 3 on sensor orientation. Anyway, that's the background to doing a test program. Let's get to it. So I would likely start with the Alberta 1987 average data set. I would deconstruct it from scale distance to distance for the potential charge sizes I might use. And again, you can see that the 1 kilogram charge size using the metric system is exactly the same as the scale distant result. Then I would look at it in its linear format. It's a bit more intuitive as to the energy falling off rapidly in the near field. Then I would look just, let's say, specifically at 1 kilogram if that's what I was planning on using, and I would look at the average data set and the outlier, and then I would consider the structures that I have in the area and other obstacles where I may be losing coverage. I would determine how close I need to get and consider using a smaller charge when in close. And this could affect what all I would use in the testing. So I would probably want to have offsets in this sort of range as indicated by the red stars. This would capture 150, 150, 30, 15, 7, and 4 millimeters per second. Larger charge sizes often require more test locations to capture the entire relevant PPV range. And then this slide is just showing exactly the same thing, but on the logarithmic plot. And perhaps it's very intuitive to others, but for me it's not quite as intuitive, but they do plot out with a nice distribution, therefore nice plotting later on. Okay, so let's look at some actual 0.125 kilogram tests. So this is the 0.125 average and outlier that I have from my Alberta data set, and this is probably what I would use. So for a small charge, I would use 6 test locations at 2, 4, 8, 16, 32, and 64 meters. I would always recommend having at least 2 instruments for testing in case one fails, especially if the location is remote. That way your 6 data points become 12. Now, my standard is to use 3 instruments to get good diversity of offsets without having to drill too many holes. I do have the luxury of being able to rent instruments here in Calgary and then transport them to the work site. You can conduct the tests at the start of drilling as long as the other drills are staying away from sensitive structures. I would usually do about 4 or 5 locations on a 3D and then be able to determine what we're going to use at the various offset distances. And you can see in the diagram there are 2 instruments off the end of the drilled holes and 1 in between. This gets a good distribution of offsets. The longitudinal axis of each sensor would be aimed toward the farthest source point and documented. The test area should be relatively flat and consistent geographically. If part of the test area is across changing terrain, say dry to damp, you may get varying results, which is fine. You just have to be aware. This can be valuable, especially if you're putting charges near structures in varying soil types. So make sure you have identified any sensitive structures or buried facilities in your test area before you start drilling. It's best to work in an area free of obstacles. Okay, and this is the 1 test location with the 6 shots and the 3 instruments. The plots on the left are the linear plots for each instrument, and the ones on the right are the log plots. They are exactly the same data, and the distance is plotted from the top of the hole to the sensor distance. The holes were actually 6 meters deep, so actually in the bottom 2 plots, where the offset distance is shown as 2 meters, the actual distance from the charge to the sensor is 6.42 meters. We'll talk about that right away. So on the slide to the left is a composite of all 18 records from the 1 location. The average is plotted, and so is the 95% confidence curve. On that left plot, you can see the near offset data points falling below the average trend line at the near offsets, as the trend line is predicting a higher peak particle velocity. And that is because for a 6-meter hole that is 2 meters offset, it's actually a 6.42 meter to the charge. And this tends to drag the trend line down. At greater distances, the charge burial depth does not affect the data as much. On the right is the same data, except the data is now presented with the hypotenuse distance, the actual distance from the charge to the sensor. So that's the charge at depth. And as we see plotting the hypotenuse data, we have a better correlation, the R2 value of 0.94 increased from the 0.89. So you just have to be aware of the two scenarios and determine how to keep it simple in the field with your surveyors and drillers. It may be more difficult to give them the hypotenuse distance to work with as opposed to a simple distance, as let's say with 1 kg they were going to drill 15 meters deep, and 0.125 kg it's just 6 meters deep. It becomes a little bit more complex, and the simpler you can keep it, the better. In any case, you don't want to push things into non-compliance. So if 1 kg was going to be my standard charge and I knew I might use 0.125 kgs for infill or to get closer to structures, I would set up one test for both. You could set up the test to have the same scale distances. For example, a 1 kg charge at 10 meters would be similar to a 0.125 kg at 4 meters, and you could set them all up to be the same, or you could just set up the range of interest on the decay curves and do it that way. What you do not want to do is have the charges right beside each other. So you can set it up in this diagram, or you could actually have the 1 kg charges, let's say to the right of the sensors, and the 0.125 kg to the left of the sensors. Just set up the sensors so you get a good distribution of offsets. I usually do the farther offsets first. That way I can stay by the instrument and I can ensure everything is working. Once the charges get closer, I have to retreat beyond 30 meters at a safe distance and just beyond where the blaster is operating. And make sure that people working in the area are not walking around and disturbing your sensors. Also make sure you set the sensor trigger threshold low enough to capture the far offset data with the small charges. And this is where predictions from the available data come in handy. This slide demonstrates the two charge sizes and the resulting PPV based on the theoretical equations. For the 0.125 kg charge, I introduced some small errors to make it look a bit more realistic. But in essence, if we wanted to stay below 12.7 millimeters per second, then with 1 kg, we would have to stay at least 37 meters back, but we could come as close as 13 meters with 0.125 kg. Okay, now this slide is converting those two data sets to scale distance to compare them. Of course, there's no difference in the 1 kilogram charge, but we can see that the 0.125 kg charge falls nicely on top. And that is why we use scale distance, although this case was fully expected to be near perfect because we deconstructed the values from the same equation. We do expect some differences, as we know the larger charge sizes generally have more energy lost to inelastic deformation, and the smaller charges use a larger percentage of their energy just in initiating. But for the most part, this scale distance works very well. And here in this slide is a real-world case of different charges at similar offsets in the same environment. This is an Alberta test case, and in essence, we can see that we would expect an average PPV of about 10 millimeters per second at a scale distance of 45, which is what we use for residences and water wells. So it is far below the 50 millimeters per second and in the range of 12.7 or that 0.5 inches per second, as I mentioned earlier. And our scale distance in metric of 45 is similar to a imperial scale distance of 100, and our 22.6 metric is similar to a 50 scale distance in imperial values of inches per second and feet. Okay, then the two main factors that were pointed out earlier were charge and distance. And this plot is to kind of show some error bars for a plus or minus 0.5 meter distance error at various offsets. And it's important that accurate measurements are taken as recorded. All measurements should be within about 1% of the measured distance. So a 50 meter offset should be measured to at least 0.5 of a meter, but you can set your own standard. But you can see, like with the 1 kilogram charge, we would actually expect to have about 313 millimeters per second. But if I was actually half a meter closer, I might get a reading as high as 430 millimeters per second, which would be very damaging to the data set. So charge size, or vibrator hold down, and drive level and distance are the most significant factors. Make sure you measure the distance accurately. Okay, just about wrapped up here. So what can I say? Make sure you image the steep part of the energy decay curve well, recognizing you may need more data points for larger charges. Make sure to take into account the outlier data when building a strategy for the setback distances to give you an extra level of comfort or insurance that you will not be creating any damage. And make sure that you are testing within the range you will be using, or you can distort your results significantly. So you don't have to worry so much at the small PPV values and the far offsets. You can go out to greater distances and extend that way. It's in the near offsets in the steep part of the curve where you have to be very careful. And lastly, I promise I'll get to video 3 next. So thanks for paying attention. Please consider leaving a comment or a question or contacting me, letting me know what I got right, what I got wrong, what you might want more information on, what was unclear, and it would be much appreciated. Thank you.